Hello everyone, this is Group 40. I'm Monashri. My teammates are Madhumita and Shrija. These are the topics for today's presentation. For problem statement, wildfires are increasing every day. So, old techniques like ground sensors, camera surveillance, and manual satellite images take more time and it is not efficient. So, we are this project aims to address the need for a faster, scalable, and automated solution by developing a deep neural model using CNN. The motivation is that the detection of early wildfires can reduce the spread and severity of wildfires. Satellite imagery is readily available but underutilized due to manual processing limitations. Our vision is to create a AI-driven solution that helps emergency responders and environmental agencies detect wildfires quickly, accurately, and at scale. For data source, we are using Kaggle. In For the data set, we have split the data set into two parts: no wildfire scenes and wildfire scenes. For no wildfire scenes, the images contains forests and landscapes, etc. For wildfire scenes, the images are visible smoke, fire, or both.
After collecting the dataset, we began with exploratory data analysis to understand its structure. The dataset was divided into three categories: training, validation, and test set, with balanced number of wildfire and no wildfire images. So this balance is actually important to ensure that the model doesn't become biased towards one class. We then took pixel intensity distributions, which will be shown on the next slide. So we also plotted aspect ratio images for all the images together, and we considered this aspect ratio feature because it's crucial for real-time applications like wildfire detection projects. And CNN is also sensitive towards image shape, so we resized all of them and performed this analysis also as part of EDA. So if you observe the histogram plots of all the images using grayscale images, you will observe that there's a greater variation due to elements like smoke and flame. So this variation actually plays an important role to have more consistency in the performance. So these are the results for our base model, which is a random forest classifier. So we extracted 13 features for each image, 3 average RGB values, and 10 grayscale histogram bins. So we trained the model over 30,000 images and performed decently, achieving accuracy of around 95.3% and precision of 95.3% and recall of 94.7% and F1 score with 95.7%. So this is the confusion matrix of our baseline model. So if you see that it predicted correctly 3,240 wildfires and 2,883 non-wildfires, but it still produced few number of false negatives, which is 144 and 165 false positives. But this makes us understand that the baseline was solid and we needed deeper model for better accuracy.
Now coming to our final model, which is a CNN model, we selected a ResNet architecture to implement this model. And we selected this ResNet because it is already pre-trained on ImageNet and it is known for strong generalization on visual tasks. And deep skip connections help avoid vanishing gradients during training. Let's discuss some of the advantages we get from the CNN model. It learns high-level features such as smoke, burned areas, and vegetation changes, which enables us to generate results quickly and get more accuracy. And it detects the subtle wildfire indicators compared to the traditional models. It scales well with large and diverse satellite datasets, which is really important in real-time projects. Coming to our implementation details, we changed the final classifier model for the binary classification, which is wildfire versus no wildfire. We trained it using transfer learning and fine-tuning techniques. We also applied data augmentation techniques to improve the robustness of the data. Coming to the architecture of ResNet, It has 50 layers, and this architecture allowed the model to capture both low-level and the high-level visual cues, improving the wildfire detection accuracy. ResNet 50 contains a stack of convolutional layers with identity-based skip connections that help preserve learned features as the network goes deeper. We used batch normalization and ReLU activations throughout, along with the average pooling before the final layer. The model was trained over 25 epochs and early stopping was used to prevent the overstopping. Down below, we have an image of architecture, ResNet architecture, which has 50 layers. Now, coming to the next slide, these are the results that we obtained on training the ResNet. The ResNet model achieved an accuracy of 97.1%, precision of 97.4%, and recall of 96.8%. Compared to the random forest baselines, ResNet demonstrated a clear improvement in both accuracy and robustness. Fall positives were reduced to 112, further strengthening in reliability for early wildfire detection scenarios. The model performed particularly well in identifying challenging wildfire images with faint smoke and distant fires. The image right side shows us that the model had the best accuracy at the epoch 8 and it was stopped in order to prevent the overfitting. These are the analysis of the model which we trained. We have a confusion matrix and we have a full classification report for the model. Coming to conclude this project compared to the traditional machine learning models and deep learning models for the wildfire detection using satellite images. As far as our random forest baseline model is considered, we used 13 handcrafted features and demonstrated strong performance with low false negative rate, crucial for early detection. Coming to our final model, that outperformed the baseline by learning spatial patterns directly from raw image data, improved recall and precision, especially in complex wildfire scenes. Combining interpretable features with deep learning shows a scalable and adaptable wildfire detection pipeline. Based on the results and performance, CNN model is promising for real-world deployment in early disaster warning and environmental monitoring systems. Coming to the prior work, none of the team members have worked on a similar wildfire detection project. However, we have experience in computer vision, neural networks, and working with satellite imagery in past projects, which will help in designing and optimizing these models effectively. These are few of the references that we used, such as the dataset and the Kaggle dataset. Thank you.